Okay, so now Bismillahirrahmanirrahim. After having looked at a bit of error performance analysis on MATLAB and Simulink, we will just take one step back and go to the correlation receiver and do one example of how the correlation receiver mathematically deals with the incoming signal. We've studied that topic, the correlation realization of the match filter, but let's go and have a look at how it actually does it. So that is our next topic. So we are doing the correlation receiver example, and for that we have to recall that the correlation receiver is basically based on this equation here. So what the receiver does is that this R of tau that represents the received signal, and the S of tau that represents a candidate waveform. So whatever are the possible candidate waveforms that could have been transmitted by the transmitter, the receiver basically performs a correlation with all of those candidates. So this integral here represents that correlation. So we will have multiple results, one for every correlator. So recall that we have m correlators, and the receiver then obtains m values, and then it picks the correlator with the highest value, and it gives out the decision based on that. So for example, let us consider a correlation receiver which receives a signal r of t, which is a sine waveform. That's the general notation, 2 pi ft plus phi, that's the general notation, and the frequency we have been given is 2 gigahertz, and the value of the phase of the received signal is 60 degrees or pi by 3 radians. So that's the first piece of information we are given. And then we are told that the digital communication system was using 4 PSK modulation with 4 possible phase states of 0 degrees, 90 degrees, 180 degrees and 270 degrees. So actually the waveform that would have been transmitted, it would have had one of these phases, but the one that we have received has got a phase of 60 degrees. So obviously while it has passed through the channel, its phase has changed. So we may say that it got affected by phase noise, as you have seen in MATLAB Simulink example. So anyways, that's what we know, 4 PSK, and these are the original phases. So they would become the basis for the 4 prototype signal waveforms, or the candidate waveforms. So the receiver uses correlators to pick one of the possible states. Obviously that's what it will do. So what you need to do is to perform the correlation with all the combinations and show which one would the correlation receiver select. So that is your task, and that is all the information that has been given to you. For simplification, you have been told that the time period capital T is 1 second. So that means the lower limit in the integral is 0 while the upper limit is 1, to simplify the things, so that you can calculate a definite integral and end up with a numerical value. So what we will be doing now, the procedure is that one by one we will find the result of correlation. Okay, so we will do it one at a time. And basically, as we have seen on the previous slide, it is nothing but an integration of the product of two sinusoids, and integration or differentiation of sinusoids is never really an issue, so it shouldn't be difficult, because we know that sinusoids have that property that their integrals are sinusoids and their derivatives are also sinusoids. So there is not a lot of complexity involved in the integration of sinusoids, so it shouldn't be difficult. So integral limits, as you know, we have discussed on the previous slides, the integral limits are from 0 to 1. That's the first thing. And what are our four prototype waveforms? As you were told on the previous slide, that the transmitter or the digital communication system, it uses 4 PSK with 4 possible phases: 0 degrees, 90 degrees, 180 degrees and 270 degrees. So based on the same, you can well imagine what will be the mathematical expressions of S1 of t, S2 of t, S3 of t and S4 of t. So basically S1 of t will have a form which will look like this with a phase of 0 degrees. S2 of t will have a form that looks like this with a phase of 90 degrees. S3 with a phase of 180 degrees and S4 with a phase of 270 degrees. Now before you proceed further with the integrals and the sinusoids and their arguments, please remember that it can be done in two ways. Either you can do all those mathematics while using the angles in degrees, or you can do the mathematics using the angles in radians. So you have to pick one and follow the uniformity. So in online calculators or in other calculators, mostly the radians arguments are used. Okay, so just bear in mind, you don't make a mistake. So you have to use the right kind of arguments for the right kind of calculation or calculator. Anyways, so these are your prototype waveforms. So basically what the receiver needs to decide that which one of them was sent. Was it the 0 degree one or the 90 degree one, 180 or the 270 degree one? It has received a 60 degree one, which is none of them. So it has to perform correlation and then basically reach a decision as to which one of them was transmitted. So that is the challenge. Okay, so now time to numerically solve the integral by putting all the numerical values in. So we put the numerical the values of the integral limits, and we put the value of the frequency as 2 gigahertz, and we use the value of phase. The way I have done, I have used radians. So when it comes to correlator 1, so basically we will be solving the integral of the product of these two sinusoids, as you can see on the screen. Okay, so we'll be solving this, and basically when you multiply them and then you integrate them, definite integral, so the answer is 0.25. So I encourage you to do these calculations at your end and make sure that you also get the similar answer. So that is the output of the first correlator. Now going on to the second correlator, the correlation is with the 90 degrees one, so pi by 2 here, whereas the received signal is this pi by 3. So the second correlator has these two signals to correlate, and its answer is 0.433. And the third correlator, that will be done with 180 degree one, so the angle here is pi radians. Okay, and the answer is minus 0.25. And the last correlator, we will use the prototype waveform with 270 degrees or 3 pi by 2 radians, and the answer for that correlator is minus 0.433. So there we have the outputs, the numerical outputs of all the correlators. And as we have studied that the receiver uses M correlators and determines the numerical outputs, and then makes them pass through a comparator, and then selects the correlator with the highest value. Okay, so after this all values are calculated, let us go on to the next slide. And what do you think, which correlator output has the maximum value? Correlator 1, 2, 3 or 4? So as you saw on the previous slide, correlator 2, that gave us the maximum value. What does it mean? That means that S2 of t is selected as the transmitted symbol. So the receiver will decide that S2 of t was transmitted. So the receiver decides that this form of the carrier which was received with frequency 2 gigahertz and the phase angle 90 degrees or pi by 2 radians. That was the transmitted symbol. So anyways, by looking at the phase angles of all the candidate or prototype waveforms, you would have probably arrived at the same conclusion even before solving the integrals. But numerically that is how the receiver does it. So it performs a correlation and then it takes the decision, and that is very much in line with the principle of maximum likelihood that we discussed. But it could get tricky if some other angle is received. So the same example, if you try with 45 degrees, you will come to know that there could be scenarios for receiver where it could become confused as to decide in whose favor. Okay, so now I bring you back to the basic block diagram of a digital communication system. So as you know that we have probably done every single block. So we started with our discussion that if the information is in some other form other than electric form, then a transducer is used to convert it to electrical signal, which is analog, and then if the signal is analog, then it is first converted to digital signal, and within analog to digital conversion, then there are 3 steps. There is sampling, there is quantization, and then there is encoding. And after encoding, then we finally have the bits, and then the bits need to be represented by a waveform, and that's where the line coding comes in. And then some books consider all these steps as part of source coding, whereas some books consider that these steps come here, and source coding basically involves encryption or compression. So once we have the information in bits or digital form, we might go for compression or encryption if needed. And then we have the next block, which is channel encoder, where we introduce extra bits which will be used later for error detection or error correction. And then we also discussed interleaving, that is there, and multiplexing, that is there as an optional block. And we discussed then different types of modulations, digital passband, digital baseband modulations. So basically then we have the modulation block. So we've discussed them, and right now we discuss the problem, the example of a correlation receiver, which is basically deciding that once you have the signal received through a noisy channel, it should be able to relate that which of the prototype waveforms was it. And once the receiver knows which of the prototype waveforms was it, then it is able to basically demodulate it, convert it back to the baseband waveform, which is in the form of digital waveform, which is bits. So basically here the information may be analog, and then it is converted to bits. So here the number of bits are reduced or encryption is done, and then here the number of bits are actually increased as we are adding more parity bits. And then here those bits are used to modulate an analog carrier when talking about wireless communication, and then that analog carrier is obviously it is modulated, so it is sent through the channel, and we have noisy channel. And we also discussed channel effects, ISI and noise. So ISI and AWGN, we analyze them independently, how they affect the channel, how we can deal with it, and basically we need a receiver which can deal with both noise and ISI. And so we discussed AWGN, we also discussed noise, different types of noise, and then the demodulation. The receive filter, the receiver, the 2 main processes at the receiver, one is demodulation and detection, and the other is the decision making. So first we demodulate and then we make decisions as to whether the bit is 0 or 1. And then we come to channel decoding. We've discussed it, that how we encode and then how the receiver decodes. So for example, when we discussed Hamming, we considered Hamming encoding. We also discussed Hamming decoding. Similarly, when we discussed CRC, so we considered CRC encoding, and we also considered CRC decoding. So while we have been discussing the digital communication system, we have been discussing what will happen at the receiver. So what will happen at the receiver? So we've discussed them. Similarly, for convolutional encoder we discussed Viterbi decoding, so that's what we have done as well. Okay, so while we were going through these blocks, we were also discussing their opposite processes that would happen at the receiver. And then after channel decoding, obviously once error correction or detection has taken place, the data bits will be passed on to source decoder. So if there was compression, it will be decompressed. If there was encryption, it will be decrypted. And once that is done, then it will be passed on to the output transducer to convert it to the form it was in. So if it is for audio signal, it will be converted from electrical signal to audio signal. So for example, so on. And if there was analog to digital conversion here, there will be digital to analog conversion here. So that is probably the only thing that we haven't discussed right now. So that is what we are going to discuss next. So we will be looking at basically digital to analog conversion. So we are here, we have our message in digital form, in the form of bits, and now we are trying to convert it to an analog form. So we use digital to analog converter, which is our next topic. Okay, so that brings us to digital to analog conversion, which is our next topic. And basically data which is in binary digital form, it can be converted to analog form by using a summing amplifier. So we have studied the hardware that can do digital to analog conversion. It is just an application of amplifier, a summing amplifier that we studied a couple of semesters ago. So a simple 4-bit digital to analog converter can be made with a 4-input summing amplifier. So you just need multiple inputs of the summing amplifier. If you want to convert 4 bits to analog, you need 4 inputs. If you want to convert 8 bits to analog, you need 8 inputs on the summing amplifier. So the main hardware is summing amplifier, and the number of inputs to the amplifier, that depends on how many bits you want to convert to analog at one time. So in this example, we are going to discuss a 4-bit digital to analog converter. But here is a note of caution that this type of digital to analog converter, it's not satisfactory for a large number of bits, because it requires too much precision in the summing resistors, as you will see on the next slide. So when we move on to the next slide, you will see that if there are a lot of inputs, then the design or achieving the very precise values of resistors, that becomes an issue. So here is our 4-bit digital to analog converter. So basically because it is 4 bits, so it has got 4 inputs here. This is your inverting summing amplifier. As you can see, the input is on the inverting terminal here, and the positive terminal is connected to ground, no input here, so it becomes an inverting amplifier. And it is 4 input, and the way it is working is that the resistors follow a certain mathematical pattern. So basically this is RF, and you can say this is R1, R2, R3, R4. So RF, the value of RF, whatever is the value of RF, that is the value of R1, and then R2 is half of R1, R3 is half of R2, R4 is half of R3, and so on. So this is what the previous slide was talking about, that with a large number of inputs, it becomes very difficult, rather impractical, to achieve these very precise values which are half of the next resistor. So starting from 10k, 5k, 2.5k, 1.25, the next will be 0.6125 and so on. So it becomes very difficult. So we have scaled resistances into a summing junction. This is our summing junction, and basically what is the impact of having these different resistors? So as you know that because of a different resistance here, different amounts of currents will flow. So they will contribute differently to the overall current that flows in the feedback circuit, in the feedback resistor. So basically, where the highest current flows, that will be the most significant, and where the lowest current flows, that will be the least significant. So for example, the inputs in volts here, so the inputs are in volts, they are weighted in the summing amplifier to produce the corresponding analog voltage. Okay, so we know here it is represented by binary ones and zeros, but in reality, in terms of voltages in the circuit, the ones will probably be represented by 5 volts and the 0 will be represented by 0 volt. So these are all high and this is low. So it is decided that the high will be represented by so and so voltage and the low will be represented by so and so voltage. And you know the equation for the summing amplifier, inverting summing amplifier. I'll just try to repeat it. Okay, so V out is basically minus RF and then we have brackets V1 over R1 plus V2 over R2. You can verify this equation from your previous notes, but I think that it was the same, plus so on. So this is basically the expression or the equation for the output inverting. Okay, and because all the resistor values are different, so they will remain here with their respective voltage. So this voltage by resistance, basically this ratio, that represents the current. Okay, so for example, if the voltages are 5 volts, so wherever there is a 1 there is a 5 volt, and wherever there is a 0 there is a 0 volt. So consider these two, for example, 5 volt or 5 volt. So the voltages are the same, but the resistance values are different. So the resistance, so the expression with the lesser value of resistance, that will give us greater current. This will give us greater current, so that will have more contribution in the overall current here as compared to another current where the value of resistor is high, so the value of current will be low. So for example here, so the current contribution from this branch is less than this, which is less than this, which is less than this. So this sort of becomes the most significant and that becomes the least significant. So here what the calculation has been done is that minus RF over R1, if talking about this resistance here, and we take it as 1. For simplicity, let us take it as 1 volt and this is taken as 0. So if this is 1 volt, this is V1, so the value 1 goes here. RF is 10 kilo ohm, R1 is 10 kilo ohm. Okay, so the answer is, so you can simplify, the answer is 1 here. Okay, after simplification, the answer here is 1. Similarly, if you calculate this second voltage, that is 0. So whatever the value of resistance is, it doesn't matter because the voltage is 0. Now the third voltage is 1, whereas its resistance is 2.5. So it's basically 1 divided by 2.5 here, and there we have got RF, which is 10 kilo ohm. So here is 10 kilo ohm here, there is 2.5 kilo ohm here, the net result is 4. So that is why you see a 4 getting multiplied by a 1. And then similarly the fourth one here, you will have an 8. So when you combine all of them, the output is minus 13 because of inverting with the minus sign. So the output is minus 13. So with this combination, the output will be minus 13 volt. With a different bit combination, the output will be different. So if you make up a table, if you draw or construct a table of all the possible bit combinations here, you will end up with 16 different values for output depending on the bit combination. For every bit combination there is a unique output. So that is how sort of we convert it from digital to analog using a summing amplifier. And just a last note here, that if we have a 12-bit digital to analog converter of this type, that would require the largest scaling resistor to be 2048 times the smallest. So this approach quickly becomes impractical. So it is not a very practical design of a digital to analog converter. That's what we must keep in mind. Okay, so now we come to the second type of digital to analog converter, which is more practical design, that is known as the R2R network digital to analog converter, or R2R ladder network. So the problem with the summing is overcome in this design. So you see, with the summing amplifier we needed in the exact multiple or exact half of the previous resistor. So that thing is not required here. So basically the way it is constructed is that there are only two values of resistors required. So whatever is the value of R, we need 2 times R. So it's basically R2R, 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 as you can see here. So that is a R2R ladder network digital to analog converter. And once again the principle is the same. It could be inverting, it could be non-inverting, it doesn't matter. Okay, but here is our reference voltage connected to every input, and every input is also connected to ground. So every feed here to every resistor, it can either be connected to ground or it can be connected to the reference voltage Vref, as you can see here. So the switches are shown with the option of either connecting to Vref or connecting to ground. It's the same thing, just represented in a different manner. So basically whichever bit is high, that will be connected to Vref, and whichever bit is low, that will be connected to ground. So a 0 would mean it is connected to ground, and a 1 would mean that it is connected to Vref. Okay, so obviously depending on the bit combinations, some of them will be connected to ground and some of them will be connected to Vref. And this shows you the order of the bits, most significant and least significant. And you can also make it out from this simplified expression here. So which of them has got more contribution in the overall output voltage? This one has. So that is the most significant here. And this one has the least amount of contribution in the overall output voltage. So that is the least significant. So same arrangement as was in the previous case, most significant to least significant, but this has the additional benefit that only R and 2R values are required. And because of this R2R, the expression is simplified. So you can go on and derive, it's a basic summing amplifier equation but simplified because of R2R combinations. Anyways, so this is the expression for output. So once we decide what will be the value of Vref, then we are able to obtain the values of output for different combinations of inputs depending on whether they are high or low. So that is the other type of digital to analog converter. Once again, we will end up with a table for all the bit combinations. So if we are talking about 4 bits, so we'll have 16 combinations. So we can make a table and see that what will be the output for every combination. So that is how we are able to convert digital values to analog values.